Hey, this is Dr. B, and let's review for the gases test. Each of you has been given a gas, and you should know how to apply some changes to that gas to see what will happen. The changes can be pressure, volume, or temperature, and the relevant formulas you should know are Boyle's law, Charles' law, and Gay-Lussac's law. Those involve changes in pressure, volume, or temperature where one of them remains constant. Like Boyle's law, the temperature is not changing, but as the pressure goes up, the volume goes down, and vice versa. Charles's law involves constant pressure, but as the temperature goes up, the volume will go up, and vice versa. And the units are fine for these formulas except for temperature. Make sure you're using Kelvin for your temperature. Gay-Lussac's law, volume does not change, so it's a container that cannot expand or contract. And as the temperature goes up, the pressure will go up. Think of it as a dangerous law. We can combine these like this, or if temperatures changes in pressure, volume, and temperature. Remember, use Kelvin for your temperature. And for systems that aren't changing, you can still apply the ideal gas law. Let me fix this here so you can see the whole thing. There it is. For when pressure and volume and the number of moles and the temperature are just in a container, you can solve for these things. If you know everything except one, you can figure out the other. You don't have to know R because you do know R. It doesn't change. It's just a constant. Now for this law to work, make sure you're using the right units. If you say the word lat-mul, you'll be correct. Liters for your volume, atmospheres for your pressure, Kelvin for your temperature, N is the number of moles. For example, if it were methane, CH4, 16 grams would be a mole. 12 for the carbon, 1 for each hydrogen. So those are the laws that we'll be applying on this test. Okay, let's solve a problem. If the temperature of your gas, here I'll show the whole thing. If the temperature of your gas is raised to 30 degrees, well, it was initially at 0. That sounds like it gets a lot hotter, but don't forget we need Kelvin. So we add 273 to get our Kelvin. We're going from 273 to, let's see, 273 plus 30 to 303. So we're heating up a gas a little bit. It's not to get pressurizing. Instead, it's going to get to a new volume. It's going to expand. Draw before and after pictures and show your work. I'm going to draw a balloon, which I've already started to draw. It's initially at 273 Kelvin, and I know the pressure doesn't change, so I won't bother writing that. But the initial volume, I guess, is 1 liter, 1.00 liters, and we're going to heat it up. And it should get a little bigger. 273 to 303 isn't the biggest change, so I'll draw it a little bigger. Does that look a little bigger? I hope so. And now we're at 303 Kelvin. So it's going to go to a new volume. Since we're dealing with pressure and volume, I guess that, temperature and volume, T1 over V1 equals T2 over V2. Let's go ahead and plug in our numbers. The initial temperature is 0 degrees Celsius, but I need to write Kelvin, 273 Kelvin. The initial volume was 1.00 liters, but the new temperature went up to 303 Kelvin. How do I know that? Always add 273 to your Celsius to get your Kelvin, and it's going to get a little bit bigger, maybe a tenth bigger, and I'll just call that X liters, right? How I'm going to isolate X by cross multiplying. So I'm going to write X times 273 Kelvin is equal to 1 liter. See, I'm just crisscrossing here. 1.0 liters times 303 Kelvin. Wonderful. I still need to isolate X, so I think I'll divide both sides by 273 Kelvin. Here it is on the left. Here it is on the right. Let's clean it up. 273K over 273K equals 1. K over K is gone, leaving us with liters, which I like. And the new X is going to equal 303 liters. See how that unit is left standing? Divided by 273. And let's punch that in. 303 divided by 273 equals, now everything had 3 significant figures, so I'll keep that. Looks like it rounds up to 1.11 liters. I'll circle that. That's what we expected. It just got a little bit bigger. 1.11 liters, and that's problem number 2. Okay, question number 3. If the volume of our gas is reduced to 0.037 liters and the temperature doesn't change, what's the new pressure? Well, what's happening? We're reducing the volume like crazy. It was initially 1 liter. We're going down to less than a tenth of a liter, but we're not heating it up. It sounds like the factors at play are pressure and volume. So why don't we draw a before picture that uses like a pressurizable system. So I'll draw a like a syringe sort of here, there, and we can press down on that barrel. Now initially it's 1.00 liters and it's 1.00 atmosphere, but we want to go way down in the pressure. And by the way, how do I know these initial conditions? If you're just looking at this, it's up at the top of the page. For all the questions, those are the initial conditions. All right, so we're going from 1 liter down to, so I'm going to write pressurize like crazy, 2 exclamation points. Try to draw the same size this time of our container, but let's take that barrel and bring it way down near the bottom. Now it's supposed to be airtight, so we'll just assume that it is. And now it's way down to 0.037 liters, and X should be our new pressure we expect to be very high, X atmospheres. So that's pressure and volume. P1 V1 equals P2 V2. 1.00 atmospheres at 1 liter will equal our new, let's see, our new pressure. Yeah, what is the new pressure? It's going to equal X at 0.037 liters. I'd like to find out what X is for my new pressure, and so I'm going to divide both sides by 0.037 liters to get rid of it there, which it does, but you got to do it to both sides. Fine. And I guess X is going to be equal to this number. Liters is gone. Atmospheres is what it will kick out. So I need 1 over 0.037. 1.00 divided by 0.037 equals 27.027, repeating. How many significant figures? Well, in this case, we have somewhere I think we had 2. Yeah, look, there's only 2 significant figures there. Always drop your leading zeros. So I'm just going to write 27 atmospheres. Circle it. Maybe change that to 27 so that everything looks nice. And that is question number 3. Okay, question number 4. If the volume of this system, now you might recall initially everything was 1 atmosphere, 1 liter, 0 degrees Celsius. We're increasing it to 1.5 liters. And we're also pressurizing it from 1 atmosphere to 2 atmospheres, and they want the new temperature. I see all sorts of things changing. I'm already recognizing that it's the combined gas law. And to make the volume bigger on something, you got to heat it up. And if to change the pressure to make it increase, you also have to heat it up. So I think we're going to get a much higher temperature. So why don't we draw an image first of our, since it's going to expand from 1 liter to 1.5 liter, let's draw a balloon. It's at 1.00 liters. This was given initially in the question up at the top. I'll go ahead and show you in case you needed that. There it was, the initial conditions. Make sure I can see it there. It's at 1.00 liter, it's at 1.00 atmosphere, and it's at 273 Kelvin. That's a little messy, but I hope you can see that. It's going up to 1.5 liters, so let's make our balloon 1.5 times bigger. Yeah, I'm buying that. So it's 1.50 liters, so we need to heat it up. but it also got a little bit pressurized. It went to 2 atmospheres. That's a higher pressure. And the only way you can do that is if the thing is a little resistant to a pressure change. So I guess I'll make it just a little thicker. Hope you can still see those numbers. That would be reasonable to me. You know how like a thicker balloon, it resists that change in volume a little bit. It pressurizes somewhat. So that seems okay to me. And X is going to be the new temperature. So let's write T1, V1. I'm sorry, I think it's P1 V1 over T1. Check your formula. P1 V1 over T1 equals P2 V2 over T2. How did I know that? I have a V1 is 1 atmosphere. I have a V2 is 1 liter. 1 liter, sorry. V2 is 1.5 liters. P1 is 1 atmosphere. P2 is 2 atmospheres. T1 is 0 Celsius, but I'm going to write 273 Kelvin. T2 equals X. We have 6 variables, 5 of which we know, so let's plug in. It seems like a lot, but it's not that bad. Initial pressure is 1.00 atmospheres. Initial volume is 1.00 liters. Initial temperature is 273 Kelvin. Always use Kelvin at 273 degrees Celsius. But the new one is pressurized up to 2 atmospheres and also expanded a little to 1.50 liters. And the new temperature is X. We need to isolate X. So let's cross multiply. This times this equals that times that. Give us a semicolon here. X times, I'm cross multiplying, so X times 1.00 atmosphere. I know some of you would just say it's 1 times 1, I'll skip the whole thing, but I like writing my units. Times 1.00 liters is equal to, this thing crisscross, 273 Kelvin times 2.00 atmospheres times 1.50 liters. Is that still showing up? Yes, it is. And I need to isolate X, so let's divide both sides by that whole thing. 1.00 atmospheres is gone. Also divide both sides by 1.00 liters. Let's do it. 1.00 atmospheres times 1.00 liters. Good. Look how that atmospheres cancels. Liters cancels. We are going to get Kelvin, which I like. That shows me my setup is good. And we simply have 273 times 2 times 1.5 should give us our answer because everything else is divided by 1. So clear it out. 273 times 2 times 1.5 equals 819 Kelvin. I'll circle that and I'll put it right there. 819 Kelvin. And that makes sense. We got to do more than double it. It's like I think 2.5 times in order to double the pressure and double the pressure and make it 1.5 times bigger. So we had to go from 273 Kelvin up to 819 Kelvin. Yep, and there you go. Hey, the answer is correct, but I said it was the same as doing 2.5 times, but 273 times 2 times 1.5 equals 3. So this is actually tripling the temperature, Kelvin, just to add that little detail. Hey, it's time for question number 5. What's the mass of your gas? You might recall from the initial question, you had a liter at 0 degrees Celsius and 1 atmosphere. It was OF2. We just want to know how much it weighs. Nothing's changing, and so why don't we just draw a container? We don't have to draw initial and final. We just need to know how much is in there. We know that it's at 1.00 atmospheres. We know it's 1.00 liters. We know that it's 273 Kelvin, which is 0 degrees Celsius. We just want to know how many moles that is, and in turn, how many grams that is. We can get the moles first, and don't forget that OF2 has a certain molar mass, a certain number of grams per mole, so we should be good. That means we're dealing with the ideal gas law. Anytime you have a question that's really unchanging, or if you see mass or moles, it's probably ideal gas law, so I'm going to write PV equals nRT. I know that I can get mass from moles, so I'm going to rearrange. I'm going to write N equals PV over RT. I simply got that by dividing both sides by RT to isolate N. And this is the picky law, so let's make sure we're picky. Are we pressure in atmospheres? 1.00 atmospheres. Yes. Is it volume in liters? 1.00 liters. Yes. Is R just a number? You betcha. 0.0821 liters times atmosphere, all divided by mole times Kelvin. Wonderful. And we're solving for the temperature. No, we're not. Temperature is given too. We're solving for N. Temperature is 273 Kelvin. All right, let's punch all that in. That's just 1 times 1 over this. So it looks like it's going to be, let's make sure that the units spit out moles. Atmosphere over atmosphere is gone. Liters over liter is gone. 1 over mole times nothing. Mole is still there. And Kelvin, 1 over Kelvin times Kelvin equals 1. 1 over moles equals moles. And it's 1 over 0.0821 times 273. Clear it out. 0.0821 times 273 equals 22.41 moles. Reverse it, I should say invert it, and we get equals 0.0446 moles. That's the answer right there, 0.0446 moles. But how many grams is a mole? You might recall it was oxygen difluoride. It's open notes, so I don't want to record that. Let's do that again. What is the molar mass of oxygen difluoride? 0.0446 moles times 53.996 grams per mole equals we've got 2.41 grams of OF2. Get rid of that. 2.41 grams of OF2. And that is the answer to question number 5. Question number 6. If you remove 1 gram of this gas but keep the volume and the pressure constant, what is the new temperature? This is referring to question 5 where, well, actually you could just do it from the beginning. You've got 1 gram of a gas and based on the initial conditions, we're at 1 liter, 1 atmosphere, 273 Kelvin. That means we have our grams. From that we can get our moles. So we have our N, we have our P, we have our V, we have everything except the new temperature that must result. So let's just, you could try to say to yourself, things are changing, but if you do that, you'll never see initial and final conditions that have a N in it. I mean, there is one, but I didn't include it. So we're simply going to use all our final conditions, right? We have enough final conditions to just use PV equals nRT. PV equals nRT. I want T, so how about T equals PV over nR? I got that by isolating T, divide both sides by nR. And make sure you use Latmok, liters, atmosphere, mole, and Kelvin. Pretty standard conditions here, 1.00 atmospheres. And for people seeing this from the outside, they might be saying, why don't you use Avogadro's principle? Yeah, we could, but you don't have to, so we're not going to. So we have 1 atmosphere, we have 1.00 liters, we have N. which is 1/54th of a mole, right? Before we determined that the molar mass of OF2 is 53.996 grams. This is OF2 from the initial conditions. And so we have, I think I'll throw it all in here. And why don't we just say it is, well, actually, I put it over here. I'll say 1.00 grams, but 53.996 grams is a mole of OF2. So we have 1 over 53.996, which I already punched in. We have 0.01852, carrying a guard digit there, 0.01852 moles of OF2. So that's our N, 0.01852 moles. And we have an R, 0.0821 liters atmosphere. Mole divided by mole Kelvin. Checking our units, atmospheres is gone. Liters is gone. Liters over liters there. Kelvin is not gone. 1 over Kelvin equals Kelvin. And is moles gone? Yeah, moles times 1 over moles equals 1. So it's simply 1 over this number, right? 1 over 0.0185. Let's go ahead and do it. 1 divided by, doing these together, so use parentheses, 0.0185 times 0.0821. Close your parentheses, it'll do both. And we have 658, 3 significant figures, Kelvin. So now we have a balloon, drawing it, that is simply 1.0 grams or 0.01852 moles of OF2 at 1 atmosphere, and it's 1 liter. And I think that's everything. Yeah, the temperature, it's pretty hot, 658 Kelvin. And that is the answer to question number 6. Okay, the last question is, how could you turn your gas into a liquid or solid by changing the temperature? Well, we are at the initial conditions that were given initially. It's 1 atmosphere, 273 Kelvin, and we just want to turn it from a gas into a liquid or a solid. I guess we'll have to cool it down. I did look up these numbers. The melting point is minus 223. The boiling point is minus 144. So if we cool it to minus 144 degrees Celsius, we'll turn to a liquid. Anything colder than that, right? We'll turn to liquid. If we cool it way down to, what was that? Minus 223, we'll turn below that into a solid. So I'm going to draw my little thermometer here. And we started at 0 degrees Celsius. We go to minus 144 degrees Celsius. And we go even colder to minus 223 degrees Celsius. Above here, it's a gas. Between here and here, it's a liquid. And is that right? Oops, no. Gas. All the way there. Gas. Maybe I'll draw it like that. And in fact, anything above higher, it's a gas. Between minus 144 and minus 223, there it's a liquid. And below this would be a solid. That's how we answer number 7. Now there is a bonus question, number 8. I'm not going to answer it for you. I'm just going to read the question. How could you turn your gas into a liquid by changing the pressure? You got to use the ideal gas law to solve that, right? Hint, you can use a temperature at which point below that temperature it will do a phase change and solve for P. I'll leave that unsolved. Good luck with the test and email me if you guys have any questions.